So welcome to this conference on modular spaces and geometric structures. I mean, we are very happy that when we started organizing this, it was very well received from speakers, and actually we had a lot of them. And then we have this is the third time we tried. They all always have been very, willing to come. Of course, this is because it's a celebration of the work and the 60th birthday of Oscar García-Prada, as I said, this is the third time, so we are all a little bit older than when we planned to meet. So actually, Oscar is 60 plus epsilon. I didn't say how much. Okay, good. Now the COVID situation has improved a lot, so we can organize this in person as we wanted. But anyway, remember, there are still infections, and so we ask you to respect when someone requests social distance and the use of masks. Okay. I sometimes hope to forget this, and try to remember. We have already sent you some practical information, which is also in the folder. But please ask Thomas, where is Thomas, and I, the organizers, if you need anything. And in particular, regarding lunch from restaurants, we can try to help. We also ask local participants to help. In particular, people who don't speak Spanish, like vegetarians that need help, please help. Remember also, if you want to come to the social dinner on Wednesday, you should talk to Jesus, who is there, and the two Guillermo Barajas and Guillermo Ayuso. Okay, basically you have to pay today. That's unless you don't want to come. And before we start the first lecture, there has been a last-minute change in the schedule. So the second talk today, Peter Gotham wasn't able to come in time, so we asked Jack to this. So we are very grateful to him because he will speak today. That means also that Peter Gotham will speak on Friday. Okay. So thanks, Jack, for this. I know it's more work during the flight, I guess. And finally, the schedule is very tight because all people were willing to speak, and we are very happy about that. But that also means I'm already late. The lecture started the lecture has 50 minutes. Okay, 5 questions. So we should respect this. Yeah. Please start.
Okay. So thanks. So of course it's a great pleasure to be here to help celebrate Oscar's 60th birthday. It's a great treat for me. So our paths first crossed just over 30 years ago when I was a postdoc in Warwick and Oscar was finishing up his PhD thesis in Oxford. I'd done my thesis on vortices on K manifolds, and Oscar showed up in my office one day in Warwick and told me that he had done his thesis on similar things, and so of course I was delighted to find a fellow traveler. Here is, oops, sorry, wrong button. No, this one. All right, let's see. There we go. Here's the title pages from our theses. You can see the same thing, and this picture actually was not at his graduation. It was a couple of years later when he finally went to his graduation in Oxford, and I accompanied him. We instantly found common ground, and since then we've been friends and collaborators. We've never really been based in the same place for more than a few weeks, but we've met multiple times all over the world, many times. Here's some pictures from various times and places that we've met. You can see the earliest ones go back to early 90s. And the last one in the middle there is from this year in Madrid, our first time after the pandemic, getting together. And all over the world, many happy memories associated with all these pictures. So today I thought I wanted to look back and sort of revisit the mathematics that we've done together. I mean, there's sort of partly this is to pay tribute to Oscar, but I think there's also maybe a sort of an optimistic lesson that can be drawn from this story. I mean, you know, in any area of research, it's always a tricky question: how do you decide what you're going to work on? And it's sort of particularly difficult in math, maybe because there's nothing external to sort of guide you. You're not trying to figure out the way nature works or any external causes like that. So it's a bit of a tricky problem. You know, one model for how to do this is you have some grand guiding problem, some sort of, you know, quest for a holy grail that is determining everything that you do. And in a way, I'm sort of envious of people who found such a quest that sort of must make it a little bit easy. But I mean, there are other ways that you can proceed. It's certainly not the way that we proceeded. It's sort of nice to know that you can get to interesting places just by sort of following what comes up as you go along. And one thing that I'd like to show, apart from the fact that I think we found some interesting things and had a lot of fun doing it, is that really in this exploration together, Oscar went a lot further than I did. He was a much more intrepid explorer than me. And on many of the paths that we did pick, he certainly went a lot further. And he also found some directions that hadn't occurred to me. And I think it's really quite remarkable sort of how broadly and deeply he ranged in this area. So I hope that will come out. But you know, when you decide to look back, it's always a little bit dangerous. It's not clear how far back you should go. Maybe I took this to a little bit of an extreme, but I wanted to show you something about the origins of Oscar, my friend and colleague. With the help of a co-conspirator who will remain unnamed, I found some evidence from his early days. And I don't know how many of you are familiar with the latest AI tools from Google, but you know, based on everything that you could find on the web today, this Google Alpha Thoughts app has inferred what was in the young Oscar's mind. And you can see some traits that you might recognize, you know, planning long ahead, not without some anxiety maybe, but there's sort of a certain bravado there and a lot of enthusiasm. So happy to be part of that. I also looked up his mathematical origins, and with the help of the mathematical genealogy project, I reconstructed part of his family tree, not the full thing, of course. And there are a few things that I want to point out about this. So first of all, I mean, there are some sort of strange loops in this that don't occur in most family trees. we'll overlook those aspects. But also notice there are a lot of prominent names in this list. And I want to particularly draw your attention to two of them. So the first one is Katie, who you'll see as we go along, played a significant role in Oscar's thinking and in our work. So this was maybe foretold in his roots. The other name that I want to point out is the Darwin there. So many years ago, I went to a talk by Oliver Penrose, who is Roger Penrose's brother. He's also an accomplished mathematical physicist in his own right, but maybe not as illustrious as his brother. And he was sort of quite humorous about this. He recognized, you know, sort of the reflected glory that he got from that name in his family tree. But he pointed out that that wasn't maybe the most illustrious name in his family tree. He claimed that he could trace a path directly from him to Charles Darwin with just 2 small gaps. And I want to show that in Oscar's case, he actually has multiple paths directly from Darwin, because the Darwin in the family tree there is George Darwin, who is Charles's son. So you can top all of the Penrose's story. Okay. So let me get to where the story started with vortices. So, I mean, the problem does have its origin in physics, although this isn't, I'm not going to say anything about the physics, but it comes from the Ginsburg-Landau theory of superconductivity in thin slabs, where the physical quantities are an electromagnetic potential, or in our language, a connection, one form, and a wave function describing physical particles called Cooper pairs. And the physical problem is to minimize an energy functional. The F here, the F in this is the electromagnetic field strength, or in our language, the curvature of the potential of the connection. But the sort of jumping off point for us, the mathematical jumping off point, was Taubes's analysis of this problem, where he introduced complex structure on the plane, and translated this problem into finding solutions for that pair of equations on the, let's see, maybe the pointer works as a pointer. There, okay, those equations. And as a result of introducing the complex structure, you see that the wave function, or the field phi, is essentially a holomorphic function, so it's characterized by zeros, and his analysis showed that the solutions were characterized by the zeros of this function and an integer which could be computed in these 2 ways. These are the integral of the curvature, which is equal to the sum of the multiplicities at the zeros. There was another perhaps influence on where our interest in vortices came from, although at the time we weren't actually aware of this. But it's interesting to point out that vortices occurred in other areas. Apparently there was a short-lived but radical movement in the art world, founded just before the First World War, and unfortunately didn't quite survive the First World War. But vortices were a force then, and I'm not sure that we can really claim what the influence was, but you never know, things work in strange ways. I mean, in my thesis, the starting point was the challenge to try and relocate Taubes's analysis from the plane to a closed surface. I mean, we sort of quickly realized that you may as well assume that it's a Kähler manifold of any dimension, not necessarily a Riemann surface. And then you can reformulate the mathematical problem in terms of a unitary connection and section of a rank n complex bundle on the closed Kähler manifold. Again, you can formulate the problem as minimizing an energy functional, which was essentially the one that appears in the Ginsburg-Landau theory, with 2 important modifications. Instead of the norm squared of the section phi, you view it as an endomorphism of the now rank n bundle. So the term that appears there is phi tensor phi dual rather than normal phi squared. And we have to introduce a parameter, which we'll see in a minute, maybe get some more insight into. So that was a 1 in the original one, but now it's a parameter tau. After some sleight of hand that's pretty standard in complex geometry, you can convert this into a problem about finding a metric on a holomorphic bundle with a prescribed holomorphic section. And the result that was really the heart of my PhD thesis was a Hitchin-Kobayashi correspondence in this situation. So a correspondence between existence of solutions to this equation and a stability condition. Stability condition very much like the slope stability for holomorphic bundles, but now involves the parameter tau. So that's sort of the way I looked at the problem. I will say that sort of the way proofs in my thesis went were really a very big debt to Carlos Simpson's PhD thesis, where he studied a similar problem for Higgs bundles. But Oscar took an interestingly different approach to this problem, which was based on the ideas of dimensional reduction. So dimensional reduction was not a new idea, and indeed even vortices had been analyzed in this way in some special cases, but not on closed surfaces. And Oscar found a really elegant way of understanding the vortices on a closed manifold in terms of simpler objects on a larger space that has a symmetry, a group action. The larger space is the surface X cross P1. The group action is the SU2 acting on P1. And now you have to look at SU2 equivariant objects in this setting and relate them to the vortices on the surface on the base X. And what Oscar showed was that the equivariant bundles that give you the vortices are of the sort that I have over there. You can see that, so the bundles are these what I've called E hat here, which are realized as extensions of a bundle coming from the base, and a particular bundle, the degree 2 line bundle on P1 coming from the P1. And the extension classes for these extensions essentially are determined by the section phi in its realization on the base. And so in this setting, you then relate the problem on X to an equivariant problem on X cross P1. And that's what Oscar did, proved an equivariant version of the Hitchin-Kobayashi correspondence on X cross P1. I'll just point out that the parameter tau that occurs over here emerges in this setting as a parameter in the Kähler form on the base that is needed to formulate the Hermitian-Einstein equations. Okay, so just one other thing I wanted to point out about this problem, because this comes up in several places later on. So once you have this correspondence between solutions to these gauge theory equations and the stability notion, then you can construct moduli spaces. Now there's a parameter involved because the stability, for example, involves a parameter. So you have moduli spaces depending on this. The parameter has to lie in a bounded range to get non-empty moduli spaces, and it doesn't depend continuously on tau, because the one way to see that is that the stability condition is an inequality on quantities that are basically rational numbers. So it's not a continuous dependence. So you get a family of moduli spaces, one for each interval of this, each sub-interval of this range of the parameter. And often in the versions that will appear later, one or other of the modular spaces in this family will be of particular interest, and typically another one will be one that is more easily analyzed. So you'll have a situation where you have a modular space you're interested in, one that you can get your hands on, and then you want to understand how they're related to each other, to use this as a way to pass information from a known situation to the situation you're interested in. In this setting, that's exactly what was done by Michael Thaddeus in a famous paper, and we used similar ideas later on. Okay, so at this point, this is when Oscar and I met and got together, and instantly realized there was a lot we could do together. And the first thing that we did was to look at a natural generalization, which appears very natural from Oscar's dimensional reduction point of view. For the vortices, we had to look at equivariant bundles on X cross P1 of a particular form, which had a bundle coming from X, and then in the quotient here of this extension, there was just the line bundle coming from P1. But you can build equivariant bundles with another bundle in the quotient as well. In fact, this isn't even yet the general equivariant object over here, but it's the next step after the one that gave you vortices. So this is what we analyzed. And now, if you look at the correspondence between what you have up here with the extra equivariant condition, you find that down on X, it corresponds to the pair of bundles together with a map from the one to the other. So these are what we call triples. There's 3 pieces of data that define it. And so these are what we analyzed. And the dimensional reduction then is going to relate the Hermitian-Einstein equation up on X cross P1 with the equation involving a Kähler form defined in the same way. And that's going to turn into equations on the base for this object now. And so you can work out that these are the equations that correspond to the equivariant solutions of the equation up there. Again, there has to be a corresponding stability condition, and that's what we worked out what that was and showed that these corresponded in the appropriate way, which is a reflection of the Hibshин-Kobayashi correspondence up on X cross P1. So here also you get a nice collection of moduli spaces. So this picture is a little bit of a collapse of the full story, but it's in spirit, showing you what you get. Again, the parameter that's involved has to lie in a bounded range that's divided into sub-intervals, corresponding to each one of which you have a distinct moduli space. And this is in principle a useful machine if you can understand one of the modular spaces and the way they relate it. And we'll see that that will play an important role later. So at the same time as we were doing that, there are sort of a bunch of obvious generalizations or variations on this theme of a bundle with some extra data. So here's a table of sort of the state of the art in so the paper appeared in '95, but this was actually written before. This was from a survey paper that Oscar and I and Richard Wentworth and George Daskalopoulos wrote together. It sort of emerged, or the idea for that survey anyway, emerged from a very nice summer program in Durham that we were all at. And there's the way we looked at the time. And some of you in the audience will spot yourselves in the picture, and maybe a few other familiar faces. What did we do next? So there are all these various variations with the specific points of interest. We looked at 2, one of which actually wasn't on this table at the time, and the other one was. I'll talk about that in a second. So the one that we looked at, we called higher cohomology triples. So they were a variation on the triple where the third piece of information, the sort of the section part, instead of being a map from E2 to E1, or just a section of H0 of E2 dual tensor E1, you take an element of a higher cohomology group than H0. This has sort of special interest when P is 1, because now it's sort of really an extension class, and so you're looking at extensions of bundles of given type. The other thing, so at this point, this is a map of sort of the topics that we looked at, so the color coding here is that blue is what I did, red is what Oscar did, and blue and red together is what we did together. And so we started out looking at vortices, we looked at triples, and then we looked at cohomology pairs. The next thing that we looked at were coherent systems. Let me just show you they're on the list over here. And this brought us into contact with some beautiful new ideas, and a group of people essentially sort of clustered around Peter Newstead, really. In a team with Oscar, me, Peter, Vicente, Munoz, Vincent, Mekar, we investigated these coherent systems, and the sort of the point of interest for some of these and for all of us eventually was the relation between these and Brunel theory, which is what this relates to. So let me tell you something about that. So the coherent systems are a variation on the idea of a bundle with a section. These were actually introduced by Lepautier originally, I think that's accurate. So what they consist of is a rank n bundle on, so we're looking at them in the context of these on Riemann surfaces. So you have a rank n bundle, and then instead of just a section of that bundle, you have a linear subspace of the space of sections. So if you just had a section that's sort of equivalent to a one-dimensional subspace, now we're allowing that to be k-dimensional. For these also, there's a stability condition, actually a nice formulation, and nice way of looking at these is, as I said, they were introduced by Lepautier, but Alistair, King, and Peter Newstead formulated a nice version of the stability notion for this, also involving a parameter that appears in a modification of the concept of a slope of now the vector bundle together with the subspace of sections. There's the parameter. We formulated the corresponding gauge theoretic equations for this, and looked at the moduli spaces, which, so it's certainly in the case when k is less than n, so the number of sections is less than the rank of the bundle, you get a family of moduli spaces that lie in a bounded range, again, one for each sub-interval of this range. And in this context, the modular space corresponding to the smallest values of the parameter relates to Brunel loci, because in this range, the stability of the coherent system with the parameter value small implies that the underlying bundle is semi-stable. So you're now looking at collections of semi-stable bundles with a prescribed number of sections. And that's the definition of a Brunel locus. This is the modular space that has information about Brunel loci, but that's not so easy to get your hands on. But the modular space at the other end has a structure that is simpler. I won't go into exactly how, but so this is a situation where if you're lucky, you can describe the modular space at the end and understand how it gets transformed as you move down through the range of sub-intervals in the parameter space. And that will allow you to transfer information from the place where you have a good control to the place where you're interested and infer useful information. That's great if everything works. Of course, the devil is in the details, and it doesn't work everywhere. But one situation where it does work nicely is when the number of sections is one less than the rank. And in that situation, we were actually able to not only establish non-emptiness of these loci, which is a question, but also infer some extra topological data about the modular spaces and the Wilmer loci. So this is the way the map of what we did now looks. So we added the Coherent Systems box there, and that took us into this world of Coherent Systems and Bradlow theory. Oscar had also started moving in other directions at this time, so you already see how he was much more intrepid. I mean, another obvious another variation on vortices on closed Kähler manifolds is vortices on open manifolds, where instead of just vortices, you now have to have parabolic vortices. So the analog of parabolic bundles on open varieties. And Oscar and Olivier Picard had examined that situation. He'd also looked at an interesting extension of the dimensional reduction machine with Luis, where instead of P1, you now replace that, you generalize that to G mod P. And this introduced a whole slew of the variations on holomorphic pairs that arise in situations like this, depending on the G and the P, of course. So, right. I remember what I'm doing now. And so another area that we hadn't yet moved into, but which was of course already being extensively investigated by other people and was hugely important already, was the world of Higgs bundles. And we saw there was an opening to see how these objects that we had been studying fit into that world, which emerged at this time. So this is Higgs bundles on the Riemann surface. And so, okay, so for the non-Spanish speakers, I've explained the joke over here. And I put these in because I got these figs yesterday, and I must say they were the best figs I've ever had. And the bundle of Higgs here would have been bigger, except I couldn't resist. But so I think everybody here knows what a Higgs bundle is. So Higgs bundle on a Riemann surface consists of a vector bundle together with a bundle map twisted by the canonical bundle of the surface. The K is the canonical bundle of the surface there. There are moduli spaces constructed for these Higgs bundles. So it goes back to the work of Nigel and Carlos. And these moduli spaces have many wonderful features, including notably a C-star action, which is described here, where the complex number just acts by scaling the Higgs field, and also a natural function that you compute from the L2 norm of the Higgs field. I've called it a Morse function, even though the modular spaces aren't always singularity free enough for this to actually be a Morse function, but it nevertheless has useful Morse function information. The relation between these two is that the critical points of this Morse function, where the Morse theory information resides, are exactly the same as the fixed points of the C-star action. And so this technology had already been used by Nigel in his original 1987 paper examining rank 2 Higgs bundles, and Peter Gotham, who really sorry didn't make it here today, had extended this to rank 3 in his thesis, where he showed that the C-star fixed points, so the crucial points in the modular space identified by the C-star action containing useful topological information, in this situation consisted of special Higgs bundles whose structure the data in the structure defining these Higgs bundles was essentially a triple. The bundle is a sum of two bundles, and the Higgs field, with respect to this decomposition, has this block form. So the non-zero piece of information is essentially the section in a triple. So what you see here is that the triples that we have studied appear as fixed points of the C-star action on the modular space of Higgs bundles. This was even demonstrated in an even more stark version in work that Peter did on SU22 Higgs bundles. So what are they? So you can think of them as rank 4 Higgs bundles, so rank 4 degree zero Higgs bundle of a particular shape. So the Higgs bundle, rank 4 bundle, is a sum of two rank 2 bundles, and the Higgs field with respect to that has this off-diagonal form. So why are these SU22? So just very briefly, part of the marvelous structure of Higgs bundles is the correspondence between their stability and the existence of solutions to natural gauge theory equations, which can be interpreted as defining a flat connection built out of the data that defines the Higgs bundle. So for Higgs bundles of this particular sort, the flat connection that you get, which a priori is just an SL4C connection, in this case has its holonomy in this real form of SL4C. To put it another way, as a result of this correspondence, so this is sort of the heart of the non-abelian Hodge correspondence that relates Higgs bundle modular spaces to representation varieties for representations of the fundamental group of the surface that the Higgs bundles are on in the group, in this case SL4C, but so restricting to Higgs bundles of this sort, giving you the correspondence between the representation, surface group representations in this real form and the corresponding Higgs bundles. Peter analyzed this situation and looked at the minima of the Higgs bundle Morse function in this setting, where the Higgs bundles look like this, and you find that the local minima are all the Higgs bundles where one or other of these non-trivial pieces vanishes. So what you're left with is again exactly the data defining a triple. And so you get an identification of the locus of minima with a modular space of triples. So the modular space of triples involve the parameter, and there's a specific value that gives you which of these in the family of triples modular spaces correspond exactly to that. And this then gives you a useful tool for extracting information about the Higgs bundle modular spaces. So this naturally led to us getting together with Peter to look at a more general version of that, where instead of restricting to 2, we looked at a UPQ Higgs bundle. So now this is a Higgs bundle of rank P plus Q, where the bundle is a sum of a rank P and a rank Q, and the Higgs field has this off-diagonal form. So again, this corresponds to, in surface group language, representations into this group. The A and the B here are the degrees of these bundles. Remember, we're over a Riemann surface here. So we looked at these, and so what has sort of just a quick brief summary of what we found. So these topological invariants naturally break up the modular space. I'll call them sectors at this point, into sectors labeled by, I mean, P and Q are fixed, so we're various carriers of the degrees of A and B. And on each one of these, you can look at the Morse function defined by the L2 norm of the Higgs field. And you can examine its minima. And again, just as in the SU22 case, the locus of the minima correspond to moduli spaces of triples of particular sorts coming from their origin as fixed points in the Higgs bundle moduli space. This was a situation where we could hope to run our machine. So some of what you find is, so first of all, what's really important for understanding these moduli spaces is what you can call a Higgs bundle version of an invariant known surface group representation world. Toledo invariant is this particular combination of the defining topological invariants. And what we could say in this situation, it turned out that by looking more closely at the modular space of triples, we could actually carry out the program and understand what these modular space of triples look like. And so what comes out of that is that these modular spaces are non-empty and connected for the values of this Toledo invariance satisfying a bound determined by the genus of the surface and the P and the Q in this case. Furthermore, so here you have a situation where there's a natural invariant that has an upper bound, and so there's a notion of maximal. And in the maximal case, the moduli spaces have special features that emerge that depend on whether P is equal to Q or not equal to Q. If P is not equal to Q, then there's a certain, we call it a rigidity. The modular spaces actually have smaller dimension than you might expect. But when P equals Q, something interesting happens. Extra structure emerges in this situation, and you get an identification of the modular space in this situation with a modular space of new objects that are like Higgs bundles, except instead of the Higgs field having a twisting by K, it has a twisting by K squared. The P and the A here are rank and degree of a bundle. So these are like GLPC Higgs bundle twisted by K squared. And this was an example of what we called Cayley partners. We won't go into the origin of the terminology. You can ask Oscar about that at tea time. But there is a good motivation for calling these Cayley partners. And this was, I think, the first Higgs bundles instance of these being identified. So this brought us into contact with various streams of ideas that certainly were new to me, but also brought us into contact with new community of mathematicians that all turned out to be very fruitful for us. But so some of the things that led to this. So first of all, UPQ is a real form of GLP plus QC. There are lots of other real forms of other interesting complex groups. So that suggests lots of other sorts of Higgs Higgs bundles to try and subject to the same sort of scrutiny. The non-abelian Hodge correspondence that I mentioned before, which relates modular space of Higgs bundles to surface group representation varieties, means that whatever, that there's a possibility of transferring information across this non-abelian Hodge bridge. So what we're learning about using Higgs bundles tools has relevance for studying these surface group representations and their representation varieties. And in fact, more or less at the same time that we were looking at, looking at the UPQ Higgs bundles, there was very interesting work going on the other side of the non-abelian Hodge correspondence. In particular, this work of Berger, Yoshi, Binhardt, who were looking at surface group representations in a situation which included the UPQ situation, where the representations are in the group of isometries of a Hermitian symmetric space. So the classical groups covered by that I've listed over here. And in all of these situations, There is a Toledo-like invariant which satisfies the bound, and going back originally to work of Milner and Wood or Toledo. What they showed, so this is a rough version of what they showed, was that the representations which are maximal, so for which this invariant attains its maximum value, have important characteristics that are similar to Fuchsian representations into PSL2R, which you can think of as the PU11 case, really. But so this means that there are components in these representation varieties which have the properties similar to Teichmüller space. And so this is now referred to as higher Teichmüller theory. And this was sort of first indication to me anyway. Well, no, actually, I shouldn't say that because there's another family of higher Teichmüller spaces that I'll refer to in a minute. But this was opening up new avenues and investigating higher Teichmüller theory using Higgs bundle methods. But I guess I should say now that the other instance where these higher Teichmüller components with characteristics of Teichmüller space first arose was in Nigel's work on not these real forms, but real forms that are split real form time. And those will come up in a minute. But so this brought us into contact with people working on the other side of the non-abelian Hodge correspondence, and led to some interesting, important meetings for us, a series of workshops and conferences that we organized or participated in. The first one was half in Strasbourg and half in Basel. This picture was actually taken in Basel. And then there was another one a couple of years later in the American Institute of Mathematics, which I don't know if any of you have visited, but at that time was a rather quirky place in the back of an electronics store. And there's a picture of Oscar transitioning from the electronics store to the Math Institute. And there was another a meeting in Singapore where the goal was to try and bring the various communities looking at higher Teichmüller phenomena together. Let's see, how are we doing? No, we're doing good.
We have like 6 minutes.
Okay. All right.
We're suddenly late.
Sure, we'll manage. So, so at this point, let's see, where were we in this map of topics? So the UPQ led us more generally to Higgs bundles with other real forms and complex Higgs bundles as well, we'll see. We examined some of those real forms, but Oscar and his students ranged much more broadly. He also looked, many of these situations are the Hermitian symmetric situation where this Cayley partner phenomena occurs, and that they had been examined on a case-by-case basis, but together with Roberto, who I think is also didn't make it, unfortunately, and Olivier Bicard, they showed how to put this on a more abstract general setting. So here's a picture of Oscar demonstrating the general version of the Cayley correspondence. One of the classes of real forms that are up at this point we hadn't subjected to our close scrutiny. We hadn't, others have, you'll see in a minute, was the real forms of the special orthogonal group, so the SOPQs, the non-compact real forms. So in Higgs bundle terms, these are ranked P plus Q bundles that decompose as a sum of two orthogonal bundles, so vector bundles with orthogonal structures. and for which the Higgs field has this particular form, again designed so that the holonomy of the corresponding flat connections lies in the correct real form. So there were various reasons why it was clear that this was an interesting class of real forms to look at. So in the special case where P is 2, this was on the list of groups of Hermitian symmetric type. So this was known already to be interesting for those reasons. The cases where P is equal to Q or Q is P plus 1 are split real forms of either the even or odd degree orthogonal groups. And so because these are split, these fell into the case that I mentioned earlier of the other situation where higher type-Miller spaces were known, where special components were detected in the Higgs bundle moduli space by Nigel by the same way in that was sort of an extension of the original identification of type-Miller space in the rank 2 Higgs bundle moduli space, namely by looking at a section of the Hitchin vibration. There were also additional components that had been identified by Brian Collier. So there was, it was clear there was a lot going on here. Also, Oscar's student Marta had looked at the Morse function, the L2 norm of the Higgs field, and had detected evidence that there were minima there that were probably identifying additional components other than the obvious ones that you might expect. Also, on the other side of the non-abelian Hodge correspondence, in the work of people investigating the higher type-Miller components there, there were notions of positivity that, and an important notion of Anosov representations that had been developed that were sort of identifying marks of the higher type-Miller components from that point of view. And in particular, this notion of positivity that Guittard and Winhardt introduced applied only in a very select set of situations, including the known higher type-Miller spaces and one other classical situation, namely SOPQ. So there was sort of that indication that there was something interesting going on there. So at this point, we expanded our team from Bradlow, Garcia-Prada, and Gotham to Arroyo, that Marta, Bradlow, Collier, Garcia-Prada, and Oliveira. We examined the SOPQs and constructed what we call the exotic components. So these extra ones that all this evidence suggested ought to be there in general for SOPQ. And you can see that there's sort of a hybrid of Cayley type information and the sort of information that parameterizes the other family of higher type-Miller spaces, the ones coming from Hitchin sections. So here are some pictures from this wonderful collaboration of the expanding group from various settings. And again, many happy memories associated with these pictures. So at this point in this map, so we had looked at SOPQ and so we looked at SOPQ, and so it was sort of clear from what we had found there that there ought to be some more abstract explanation of the machinery at work in this situation. And that's was going to be the topic of the next talk, but it's now the topic of the talk on Friday. Hopefully, Peter Gotham's going to tell you all about that. So I'll just mention that the result of pursuing that line of thought was our description of what I call magical exotic components. I'm not sure if the rest of the team still sticks with that terminology. But that's I think of as a very interesting part of the story, and you'll hear it all from Peter. But so this was so this is basically as far as I want to go in my collaboration with Oscar, but it's definitely not as far as Oscar went. So there was one other thing that I wanted, one other project that I wanted to mention, because I was particularly fond of it, and I think it sort of still has important relevance. This was a project Oscar and I did with Ignacy. Is Ignacy down? No, it also didn't come. Oh, it's coming. Oh, okay. I'll put it right there in the middle. It was a sort of a variation on the Hitchin-Kobayashi correspondence, allowing for slightly more general gauge groups. But so there was a lot more that Oscar did. So I want to show you some of the things and put in the graph with some of the other areas that Oscar pursued, and you'll see how widely it ranged. So there was work extending the idea of the Hitchin section to cases of real groups. There was a project looking at Higgs bundles in genus 1. Usually when we say our compact Riemann surface, we say genus bigger than or equal to 2. So genus 1 gets left out there. There's a lot of important work on looking at involutions. So real forms are defined by involutions, and these then give you an involution on the moduli spaces. There's also involutions on the base manifold that play a role and define what you can call pseudo-real Higgs bundles that Oscar and Indranil and Jacques looked at. There was also, he also pursued the parabolic line of thinking in various other directions. There were ideas coming out of the dimensional reduction in a more general setting that led to investigations of Higgs bundles on those symmetric spaces, again with Indranil. Didn't stop at looking at moduli spaces from the usual point of view, but introduced motivic ideas into the subject with Jochen Heimat and Sander Schmidt. And in yet another direction, when going all the way back to vortex equations on surfaces, there are versions of the equation where you allow not only the data on the bundles to be part of the story, but the metric on the base to be part of the story. And that also didn't escape attention. And let's see. Oh yeah, and then very recently, some very interesting ideas that in a way extend the ideas that go into the story about magical components, which rely on specific SL2 triples in the Lie algebra. If you relax the type of triples you look at, that leads to investigation of what they're called here. The VHS is variations of hub structure, but in Higgs bundle language, they're fixed points of the C-star action. I don't know if anybody's going to talk about that in this meeting, but extremely interesting work. And I think, yeah, that's as far as it goes. And so just to end, I wanted to end with a suitable birthday greeting. And since I've been in America for 40 years now or something, I guess I have to think of myself as an American. So I thought maybe an American greeting from the era of Oscar's birth might be appropriate. So let's see if it will work. Hold on. Okay, stand by. Oh, no sound. Oh, that doesn't sound good. It's Elvis singing Happy Birthday. Okay.
The other comments? Yeah. Are there any comments? Yes. What do you have to do? We know what I have to do.
Well, I can speak loud.
Yeah.
I just want to make a comment about your bundle of figs, right? Because there is another story behind, right? And this is, I thought you were going to allude to that. That many years ago, we applied in a joint project. So many years ago, we applied in a joint grant between the UK and Spain, the Ministry of Education. And apparently the name Higgs was very strange, maybe to the Ministry of Education. And so but we were very lucky that they thought it was a project in agriculture. They said, we are very happy that we can approve your grant on bundles of figs. I think that was the Eagles. So we really, we make a lot of progress between the UK and Spain in that project, and so I'm very grateful to the figs. Me too. Many years ago.
Yeah, exactly.
Okay, there are no more comments. We thank Steve for the nice talk.